Hi, AP Chemists. Today we're going to be talking about equilibrium.
So first of all, when we think about equilibrium, we have to remember that it's all about balance. And what's cool is that we can actually apply this concept to chemical reactions. In fact, we can define equilibrium in chemistry as when the rate of the forward reaction is equal to the rate of the reverse reaction.
Now, what exactly do I mean by this?
Well, consider the following reaction. The lowercase letters represent your stoichiometric coefficients. A and B represent your reactants, and C and D represent your products.
Now, how do we express that this is an equilibrium reaction?
All you have to do is just add the symbol. Now, to gain insight into an equilibrium reaction, we have to look at its equilibrium constant, or K. We specifically use Kc when talking about concentrations and Kp when referring to pressures.
Now, what does an equilibrium constant represent?
Well, think of it as a ratio of the units of products to reactants in a chemical reaction at equilibrium. This helps us gain insight into the relationship between products and reactants when the reaction is at this state, which can be very useful when conducting these types of experiments. And remember, we can express this in terms of concentrations and pressures.
Okay, so we know what an equilibrium constant is. Now, how do we find it?
After all, each reaction has its own equilibrium constant, and that's why it's important to be able to derive this number. So we have to consult with the glorious ICE tables. Now, don't let the name intimidate you. In fact, these tables are a lot easier than you think.
Okay, so first of all, what does this acronym stand for?
The I stands for initial concentrations or pressures for each species in the reaction mixture. C stands for change in concentration or pressure for each species as that system moves toward equilibrium. And lastly, the E represents equilibrium concentrations or pressures for each species as the system is in a state of equilibrium. If we know what we start with and what we end with, then we can use that information to find the equilibrium constant.
Okay, let's do an example. We're given the following information. 0.65 moles of nitrosyl chloride are added to a 1 liter solution. And here's our chemical equation up here. Let's construct our ICE table. Okay, now that we have our ICE table, we can begin filling in information. So, first, how much of the reactant do we start out with? Well, it says so right here, 0.65 moles in a 1 liter solution. Remember, to get molarity, we have to divide moles over liters. So, we do that here. 0.65 divided by 1 is 0.65. Okay, and then for these two amounts, we can assume that they start out with 0 molarity because it's not given in the problem. Now for the change, what we have to do is consider what's depleting and what's gaining. So here we can see that the reactant is depleting to make some product. Here we have to take these stoichiometric coefficients into account. Notice the 2's up here and how this does not have, this only has a coefficient of 1. Taking this into consideration, we can say that if we were to keep those ratios in mind, this would be depleting by a factor of 2x. Because since we don't know exactly how much it's depleting by, we just know the ratio. And this one is gaining by 2x. This one is just gaining by x. Now, taking this information, we can plug this into our equilibrium expression. So it becomes 0.65 minus 2x, 0 plus 2x, which is just 2x, and 0 plus x, which is just x. Now, if we did know our equilibrium concentrations of reactants and products, then we'd be able to find K. But right now, we can just write out an equilibrium constant expression. To write our equilibrium constant expression, we have to put products over reactants. So these two are products, 2x times x, over our reactants, 0.65 minus 2x. And then we set that equal to Kc. Perfect. Now you know how to use an ICE table.
But wait! If you thought you were done there, then you might have just failed this class.
You can't forget to add the exponents. This is really, really important. So anything that has a coefficient other than 1 is raised to the power of 2, or is raised to the power of that coefficient. Now let's say this had actually been a liquid. How would this change the problem?
When we're talking about solids and liquids, it's important to note that we actually end up omitting them from the equilibrium constant expression. This is because it's actually equal to 1.
And if we have been given a value of Kc, then we can easily use this value to solve for x. And if we have x, we can solve for these other components.
So you learned about K. Now let's talk about Q. Q is the reaction quotient, and it represents the ratio of products to reactants in a system at any given point in time, not just in equilibrium. Remember, the reaction wants to reach equilibrium, so we can compare Q to K to see whether the forward reaction is going to have to happen or the reverse reaction. Less than K, the reactants go to the products, so the forward reaction continues. If Q is equal to K, the reaction is equilibrium, meaning that there is no net movement. And if Q is greater than K, the products ultimately go to the reactants, supporting the reverse reaction.
And that's it. Now go get that A.